Click the bell icon to get latest videos from Ekeeda.
Hello friends, we have till now seen how a partial differential equation is formed and how we solve partial differential equation using integration method. Let us see a different type of partial differential equation, that is of linear type, of a specific form known as Lagrange's form. We will see how to solve such type of equations in this video. So, what do you mean by a linear partial differential equation of the first order? Let us see that. Any equation of this particular form is known as linear partial differential equation of the first order, and this specific form is known as Lagrange's form. In this particular equation, P, Q and R are functions of x, y and z. So we can say and by our standard definition, small p and small q are partial derivatives of z with respect to x and y respectively. So small p will be equal to del z by del x and small q is equal to del z by del y. Now let us go ahead and see how to solve the partial differential equation, linear one, in Lagrange's form. To solve linear partial differential equation of Lagrange's form, we will be using an auxiliary equation. The auxiliary equation to be used over here is this is the auxiliary equation that we use while solving the linear partial differential equation of Lagrange's form. Here we know that P, Q and R are the functions of x, y and z. Now let us see the actual working principle and solution of linear partial differential equation. Let this be our given linear partial differential equation of Lagrange's form, and the auxiliary equation that we have is here we solve equations 1 and 2 and try to get the solution of linear partial differential equations. Now the various methods that we use to solve this are we can solve this by grouping method, or by method of multipliers, or by combination of the above two methods. Now we will check each method one by one after some time. Before that, let us move ahead and let us assume that we get the solution of the first equation using the second auxiliary equation as so u is equal to a and v is equal to b be the solutions of equation 1, which we have got by using the equation 2, where u and v are the functions of u and v are the functions of x, y and z respectively. Okay, now how to find the final solution? The final solution will be received by combining u is equal to a and v is equal to b, which will be, or it can also be said to be, so this is our final solution. Going ahead, we can rewrite this final solution to get u as a function of v, or v as a function of u. So these will be known as final solution to our linear partial differential equation. Let us solve one example and understand this method in detail. Let us take one example to understand how to solve linear partial differential equation of Lagrange's form. Now, the given equation can be written in the standard form capital P into small p plus capital Q into small q is equal to capital R by first simplifying the denominator or getting rid of the denominator. So let us multiply throughout by x. So after multiplying throughout by x, we get y square z into small p plus x square z into small q is equal to xy square. Let this be equation 1, and this particular equation is in the form of where so we have got the values of p, q and r. Now using the auxiliary equation, we can go ahead with the solution. So auxiliary equation is let us substitute the values of p, q and r. So equation 2 is our auxiliary equation. We have dx upon y square z, dy upon x square z, dz upon xy square. Let us solve this auxiliary equation and get the solution of our first equation by integrating method. Now there are three methods which we have mentioned: method of grouping, method of multipliers, or combination of both. In this case we'll be using method of grouping. Let us see how to do that. From this equation 2, we can see that if we group the first part with the last part, that is dx upon y square z is equal to dz upon xy square, then y square can get cancelled and we will be able to integrate. Let us do that. Cancelling y square from both the sides, cross multiplying it, and now integrating both the sides. So we have integrated, we got x square by 2 is equal to z square by 2 plus, let us say, a constant c1. Simplifying it further, we can get so we have finally got x square minus z square is equal to a. We have considered the constant 2c1 as a. Equation number 3. Now let us see which other group we can form. Now from this equation 2, again let us see which other parts we can group together. We can see that if we group the first and the second part, z will get cancelled and we will be able to integrate easily. So let us go ahead. The z got cancelled. What we are left with is cross multiplying it and now integrating it further. Integrating it further, we have got x cubed by 3 is equal to y cubed by 3 plus one arbitrary constant c2. Now when we simplify this further, we get our final second part of the solution, that is So we have got our second part of the solution, that is x cube minus y cube is equal to, say, b. B has been equated with the constant 3c2. This is our equation number 4. So we have got our two solutions. One was x square minus y square is equal to a, and x cube minus y cube is equal to b. Combining these two solutions, what we get is our final general solution for the given partial differential equation. So let us combine the two. The first equation, the first part of the solution, what we had got was, this was equation number 3, and the second part what we had got was equation number 4. So we combine this and we get our final solution as f of a comma b is equal to 0, that is we get our final general solution for the given linear partial differential equation. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.